All right, in this lesson, I have it slated as review, but it's kind of new for you. You've probably seen it before if you've done a science course. Some of you I know would probably recognize it if we were talking in class. Usually when I say significant figures, I usually get a few groans because it's the thing that in a physics course, if you were in a high school or college, if you had any experience with it, it's the area where you can lose a lot of marks even though you know what you're doing for just not using the right sig figs. Now, we're going to go through significant figures and scientific notation simply because your solution answers are going to use significant figures. Scientific notation is going to randomly pop up in questions, and you need to know how to work with them. And you will also sometimes have scientific notation pop up. So it's important that you do know what they are and that you do know how to work with them. But that said, you will never be deducted points for not giving a final answer using incorrect significant figures. There is going to be a quiz after this lesson. That is the only lesson that the only time I'm really going to give you any kind of assessment that requires you to use significant figures. But it's just really good principles for knowing when to round, why to round, and then the scientific notation allows you just to process numbers that are shown in different formats. It's not difficult, it's pretty straightforward. The more times I go through it, I get to the point where why is it so confusing for people? And I think it's just getting your mind in a little different mindset. I have already told you in the past that if you're not told where to round in a question, especially if it's something that's being handed in, not so much of an issue in working with Sam, but if it's something that's being handed in, look at how many digits are in the question and use that and match it in your answer. So I want you to think of that principle as I explain to you what significant figures are, and you will probably discover where I've come up with that rule as we go through. So first of all, to start, what are significant figures? Well, significant figures are just digits in a number that indicate the actual precision of a measurement or a calculation. Now, when I was in university, we were doing analytical chemistry, which was really specific. And we used to have to go through long calculations at the end of a question to determine how accurate was our answer. Could I keep 5 decimal places or could I only keep 1 decimal place? And it was a long drawn out process. Just following the significant figure rules makes it much easier to process. And I will give you a slight shortcut that you can use, or that I would recommend you using to make sure that you kind of stay on the right track. You'll find sometimes I will forget to make significant figures matter in a question, and I'll try to make sure I include more of those. But they're just digits that indicate the real precision. So if you put a decimal zero at the end of a number, that means you care to tell me that there was nothing in the tenths place. So that would be a digit that tells me the actual precision. So if we look here, let's say we have 2.5 meters. So somebody has been specific enough to tell you that they have been precise to the nearest tenth of a meter, and anything past that would just be a wild guess. If I take that and I divide it by 3, I get 0.83333333 meters. Do all those digits have meaning? Well, if the first number is only accurate to tenths, it's impossible for the second one to have meaning in all of the digits. It's just not logical. So no, the digits in the solution don't all have meaning. So using the rule that I've given you before, 2 digits here, you would probably cut this off. At that point, you'd say there's 0.83 meters. And we will find that that actually does follow our significant figure rule. Now, significant figures only apply to measurements. So this number has significant figures because it's a measurement. Dividing by 3, just a number that doesn't have a measurement attached to it, that number doesn't have significant figures. It's like dividing something equally in thirds. You need to know what the original measurement is, but the 3, well, it's in 3 equal pieces. You're splitting it apart. You just need to know what part of the original measurement matters to keep. All right, so another example of a number that wouldn't have significant figures would be pi. Pi, you don't have to worry about sig figs for, because it's a known number. It's like dividing by something that's, I was going to say constant. I don't know if that's the right word to use, but it's something that's exact. It's an exact number. All right. So as we do sig figs, we're just going to be eliminating all of the digits that don't have meaning. So first of all, what digits are significant? We're going to go through, I've got 5 examples of digits that are significant or are not significant. So there's 3 rules. First, non-zero digits are all significant. So if somebody gives you a number and there's no zeros in it, all 3 of these digits, we would say this has 3 sig figs. Oh, sorry, 3. Apparently I can't count this morning. Let's change that to a 4. This has 4 sig figs. Okay, so 4.4 and 125 thousandths has 4 sig figs. Because there's no zeros, every number that's not a zero will be significant. So that's the easy one. Now we get into, okay, well, why are you specifically leaving out 0 in this case? Well, zeros are special. Any 0 between 2 significant digits are significant. So this 0 is in between 2 numbers. So it counts. It is significant. So this one has, again, 4 sig figs. All right. Any trailing 0, any final 0 or a trailing 0 in a decimal only, so not at the front of a decimal, the trailing zeros in a decimal are significant. So this is at the end of a number. There is no significant digit past it. There's no other number after it, but because it's at the end, it counts. So this one also has 4 sig figs. I'm not sure why I picked numbers that all have 4 sig figs, but we'll get to some that don't. Another example of a 0 that would count would be, let's say I have 1.00. This 0 is at the end. It's a trailing 0 in a decimal, so it counts, and because it counts, everything in between does. So this one and this one. So this would be a 3 sig fig. Okay, so not overly complicated. Everything that's not a 0 count. If it is a 0, you're going to look and see, is it between 2 numbers or is it at the end? If it's at the end, you count it and everything up to the numbers. Okay? What about the ones that you're not going to count? Which digits are not significant? Well, zeros at the end of a whole number are never significant. So if I say 4,500, 4,500, these zeros aren't significant. The only way I can say, I'd have to use special notation to show that they matter. And to use special notation to show that they matter, I would say like 450. Sometimes you put a little line on the top, 0. And that shows that that 0 has to be a 0, and it's an exact 0. It's a 0 that's not a guess. It's a precise 0. Okay, it's not like it's been rounded off. So that would be another way of showing that. But in the first one, this one only has 2 sig figs. I'm going to say SF instead of writing it out each time. If I write it like this, that would give me 3 sig figs because of the little line on top. Now, I don't think Sam will let me put a little line on the top, but that would be one way of showing it. So just in case you're wondering. And if you have the other zeros that don't count are space holding zeros on numbers less than 1. So any zeros in front of a decimal number are considered non-significant. So you basically take all the zeros that are in front of a decimal. Okay, so there's no numbers in front here, so nothing there counts. This is a number less than 1, so this 0 is considered a placeholder, it doesn't count. This 0 is considered a placeholder, it doesn't count. I start counting my digits once I hit the first number, so this one would be 2 sig figs. So it's not really complicated. The only time that you really have to think about it is, are they at the end of a whole number or the beginning of a decimal? Everything else is going to count. So let's just take a quick gander at a few questions and we'll decide how many sig figs in each. Well, A, There's no zeros in there. So let's just count the digits. 4. So if you see that in a question and you've done a bunch of math, and this is the smallest number of digits that's in a question, you can look at that. We'll round to 4 digits at the end. B, 7.04. Well, this 0 is in between two, this counts and this counts, so the middle one counts as well. So this would be a 3 sig fig. 406, same thing. A 0 sandwiched between two numbers, it counts, so that's 3 sig figs as well. Let's look at this one. Well, the 1 counts and the 5 counts, so everything in between counts. These two zeros are at the end of a decimal, so they both count. So in this case, we have 6 significant figures. That's not a very common thing to encounter. Just going to say, it's not very common to encounter that. In this particular question, okay, we have zeros in front of the decimal. They never count, so we'll take them out. The 3, we start counting at the 3. The 4 we know counts, so the 0 in between them does. And this one at the end, it's going to count too, so it has 4 significant figures. And for the very last one, I think I must have liked 4,500 because we used that number again. This one is a 2 sig figs because the 2 zeros at the end do not count for us. All right, so pretty straightforward. Well, what about using them in math? So I'll give you the specific rules, and then I'll tell you my shortcut that I'm going to say. You know, when you can't remember the rules, follow this. So for adding and subtracting, when you're adding and subtracting, the smallest significant digit that all values have in common is the lowest significant digit in your answer. What this basically says is, look at your question. Whatever the smallest number of decimal places is in the numbers that you're given, give that number of decimal places in your answer. Example 2 is going to throw a monkey wrench on that, but that's okay. So if we look here, well, 3 is a significant digit, and it's 2 decimal places in. There's actually 3 decimal places with the 3.484, but the last digit that they have in common is the hundreds place. So my answer is going to round to the hundreds. So if I calculate this out, we're going to get 8.714. And because hundreds is the smallest common place, we have to round to hundreds. So we're going to round to there. So our answer, correctly rounded, would be 8.71. Well, that's pretty logical. You can't be more precise than the least precise number. I think I remember saying something like that the first semester. I'm sure I have said something like that the first semester. You can go back to one of those early videos. Okay, let's look at the next one. What about this question? We have 1,050 minus 326, and it would really help if I did the math correctly. I added these together when I did up my solution sheet. That's what happens when you work in the evenings. So in this case, 1,050 minus 326 gives us 724. 724. Okay, let's figure out where should we round to. Well, there's no decimals here, but the question says the lowest significant digit. So this counts, and this counts. This one does not count. So we are going to round to the tenths place because the ones place doesn't count in the 1,050. Now, you will not see this kind of a case very often at all, but once in a while in an answer key, you'll see something similar like that, where they'll round to the nearest tens in order to show that. So in this case, this would correctly round. If I want to show actually how accurate this is, I would say 720 would be the answer. So I would round to the tens because the ones place wasn't significant. And I just put a 0 at the end and it's still not significant. Okay, so now the adding and subtracting one is a little bit funny for people. And I say, you know what, if you just follow the multiplying and dividing rule, I'm more than happy. So I'll give you the multiplying and dividing rule, but that I can say I covered it. Okay, I can say I covered it, and you'll see a couple of examples that have questions like that on the SAM quiz. All right, well, what about when you're multiplying and dividing? Multiplying and dividing, your answer will always have the same amount of sig figs as the value with the lowest number of sig figs. So this is the easiest one to do. You don't have to think about operations a whole lot. And when you have multiple operations in a question, so let's say you're adding, subtracting, multiplying, and dividing, when there's multiple things to do, I'm going to tell you always follow the multiplying and dividing rule. So in this rule, all we have to do is count how many sig figs are in each number that we're multiplying. Now I should really have units on these, but for the sake of simplicity, I've left the units out. So here we have 2 sig figs. This one has 3 sig figs, so my answer will only have 2. So 12 divided by 3 gives me 4. I need 2 sig figs, so I'm going to say 4.0. That shows there's 2 significant figures. Example 2. This one has 3 sig figs, this one has 3 sig figs, so our answer is going to also be 3 significant figures. And in this case, well, if we multiply them together, we get 16.128, 16 and 128 thousandths. 3 significant figures means 1, 2, 3 numbers stay, these 2 go, and rounding that leaves us with 1/16 and 1/10. So you'll notice we actually have 1 less decimal place in our answer. And that's okay. That's how the rules for what we call propagation of error work. So basically, it doesn't mean we're more precise than we should be. I know most of the time you're not going to worry about it a whole lot, but it is something that, according to the books, is something that should be covered with you folks. So I just cover it very briefly with you. Okay? So this is a 2 sig fig question, and this one is a 3 sig fig. Now the very last piece is I want you to know what scientific notation looks like and how to read it. I'm not as worried about you putting it in your calculator, but I will give you a couple tips for putting it in your calculator. Because calculators vary, I know not all of you will be familiar with it in your calculator, so please touch base with me if you get to the point where Andy's using it and you can't figure it out in your calculator. He will expect you to know how to use it. He'll assume that we've done all kinds of it. It's not something that we use a lot of, so you might not be as familiar with it as you could be. So scientific notation. Scientific notation is simply a way of rewriting numbers using powers of 10. So we often don't want to write all the extra zeros. So it eliminates all the non-significant zeros. All right. And I've got a note here. If it has a negative power, we're going to find the decimals move to the right. Positive power, the decimal's going to move to the left. So we're going to be writing our numbers to look like C and D here. So we're going to start with A, and we're going to figure out, well, how would we write that? So the number always only has 1 digit in front of the decimal place. So we're going to move our decimal here. Okay, so we're going to start with 5.4. And okay, we can't just change 54 million into 5.4. We have to tell it, well, times how many tens? Well, in order to figure that out, take your decimal. The decimal used to be here. We've moved it 1, 2, 3, 4, 5, 6, 7 places to get it to the 5.4. So by moving it 7 places, let's move 7 places to the left. So it's going to be a positive power, and we're going to say times 10 to the power of 7. It's pretty easy. B. This one, these zeros are all insignificant, so we're going to take it and we're going to move the decimal. There's always only 1 digit in front of your decimal in scientific notation, so we're going to move the decimal here. So we have 3.54. Now I have to say, how many times do I multiply by 10? Now, in order to give us a decimal less than 1, we're moving our decimal in the opposite direction, so we're going to use a negative power. Now, there's some reasons for that. If you want to know the reasons for that, I'll give you the details. But at this point, I think you can probably just trust me on it, and I can explain exactly why it would give you a negative decimal if you don't remember how your powers work. At a later point, drop by my office, come say hello, and we can have a geeky math conversation if you want it. So we're going to take our decimal and we're going to move it 1, 2, 3, 4 places to the right. I always have to think left and right. So we're going to have 10 and it's 4 places. So it's going to be a -4 because that number is less than 1. Okay. So move to the decimal in the opposite direction. So they're pretty easy to write in scientific notation. I'm not expecting you to write your answers in scientific notation. It's completely up to you if you do that, but you will see questions like C and D where you will have scientific notation. You need to know what it looks like and how to use it. If you struggle with it in your calculator, putting the scientific notation in exactly as it's written, you need to be able to write it out the long way. So 1.23 times 10 to the power of 3. How do we write that out the long way, like A or B? Well, a power of 3 means this decimal has been moved to, it was originally moved to the left, so we need to move it back in the other direction. So we're going to move it to the right 3 places. We've got to put it back. This number was originally larger than 1. So we're going to move it 3 places, and this would be 1,230. So just basically reverse the orders of these when you're putting it back into regular notation or standard notation. There's probably a technical term for that I'm forgetting. 4.7 times 10 to the -4. -4 means this was less than 1. So we need to put this back to a less than 1 status. In order to make it less than 1, we're moving our decimal 4 places. If it's going to be less than 1, we need to move the decimal towards the left. So we're going to have 0.00047. All right. Now on your calculator, if you are looking for how do you put in scientific notation, you will find usually there's a button in your calculator. You're going to look for EXP or EE. Now your calculator may automatically convert some of these. So if you were putting in, let's say you're putting in C, you would type in 1.23, and instead of putting time, you don't put the times 10 or anything, you're going to press this EXP button or EE button. You're going to press that button, and then you're going to tell it 3. This EXP, these 2 buttons equal times 10. The power that you put in after is what your scientific notation power is, and that your calculator may automatically convert that for you. For this one, I'm guessing it probably would. It would probably automatically go to 1230. But that's how you would do your scientific notation conversion. So just a few simple, really simple concepts, really simple basics that you're going to see come up. It just makes a good little refresh. The significant figures is a good refresh on rounding. And I'm going to give you a few questions to do with rounding. And then we will move into our regular physics.